So now let's look at sliding window problems where we need a variable length window. And let's take a look at a really simple example. We're given some input array of numbers. We want to find the length of the longest subarray that has the same value in each position. So essentially we're looking for the longest string of duplicates. Here we just have a single 4. There's no duplicates next to it. Here we have 2 2s, and here we have 3 3s. Of course, the longest window is this one. Now, the simple way to solve this problem with a sliding window would be to, initialize the left and right pointers. In this case, they can be at the same position because this is a valid window. And then we would increment the right pointer. Now, at this point, we would see that the right pointer is not equal to the same value as the left pointer. So that's a problem. We want our window to have the same value in every position. So what we should do is increment our left pointer until it's equal to the same value as the one at the right pointer. In this case, we only have to increment the left pointer once because then it'll be at the same position as the right pointer. And of course, then they are the same value. And then we would increment our right pointer again. And now it's here. It's the same value as the one at the left pointer. So this is a valid window. And by the way, we're going to be keeping track of the length of the longest window. Before, the longest window was of length 1. Now we found one that's of length 2. So now again, we're going to increment our right pointer over here now. This is our window. Is it valid? Well, this value is not the same as this value. So this is not a valid window. We need to make it valid again. What should we do? Well, like I said, we want to increment the left pointer until the left value and the right value are equal. So now the left pointer would be over here, but these two values are still not equal. So our window is going to continue to slide. In this case, these two values were chopped off, and this is the new window. So now that our left pointer is over here, this is our window. It's of length 1. It's definitely not the longest because we earlier saw a window of length 2. But now we're going to once again increment our right pointer. Now it's over here. These two values are the same. This is a valid window of length 2. Now we're going to increment the right pointer again. These are the same. So this is a window of length 3. And that is the longest that we've seen so far. And then we would once again increment our right pointer, but now it's out of bounds. That's how you know we can stop. So what we would return as the longest length would be 3 in this case. And the code for that would look something like this, where we initialize our longest length to be 0, and we set our left pointer initially here, and our right pointer we could initialize to 0, but since we're iterating through the entire array with a for loop, we pretty much get that anyway. And what we're trying to do here is take our window and keep increasing it until we get to a point where we can't grow it anymore. And at that point, we would start shrinking our window from the left side. But actually, what I didn't show when we were walking through the example is when we were at this point, we had a valid window. Then we found a new value that was not equal to the one over here. We actually don't need to take the left pointer and increment it by 1 because we know that if we just found a new value here, that all the other values here were duplicates. So instead of taking this left pointer and incrementing it by 1, we can immediately set it to the right pointer. And that's what we do in the code. It doesn't really change the time complexity. It's just that this is such a simple problem that we don't need an inner loop. But I'll touch on that in the next example. And on every iteration, we calculate the length of the window. So if this was our window over here, we know that this is index 0. This is 1, 2, 3. The size of our window is 3. We can calculate that by taking the right pointer, subtracting the left pointer, which gives us 2, and then we add 1 to it. That's just how we calculate the length of this window. Because we got a result of 2, we know that's not the case. This window is of length 3. That's why we have to add that 1. And this problem is actually simple enough that we don't really need the sliding window. At least we don't explicitly need a left and right pointer. I'm just doing this to kind of show you the main idea behind the sliding window. I encourage you to try to rewrite this solution without even using left and right pointers. If you get stuck, feel free to post your code in the Discord. But now let's look at a more complicated sliding window problem. Now, given an array of all positive integers, we want to find the minimum length subarray where the sum is greater than or equal to some target value that we're given. And given a problem like this one, you would want to pay special attention to the fact that all values in the array are positive. When you're given a detail like that in an interview question, it's usually not arbitrary, unless you have like a really evil interviewer who is just trying to trick you. Usually a detail like this indicates something, and it's sort of a hint at what the solution could be. And in this case, we're trying to find the length of the subarray itself. In this example, let's say the target is equal to 6. Now, the obvious brute force solution would be to go through every single subarray and find all of the subarrays that total up to 6, and then among those subarrays, keep track of which one had the minimum length. So running through that quickly, it would look like this. This is one subarray, it's smaller than 6. Let's add another value to it. This is 5, it's still smaller than 6. Let's add another value to it, 6. It's exactly equal to the target. Well, what's the length of this subarray? We would just get the beginning and the ending index and easily calculate it. The window is of size 3. So that's our minimum length so far. Now, paying attention to the fact that all values in this array are positive, we can continue to grow our window. Our window is starting over here. This is the left pointer. We can continue to increment our right pointer and grow this window. But let me ask you something. Starting from here, are we ever going to find a window that is smaller than length 3 that satisfies this condition? Definitely not, because all these values are positive. We already have a window that sums up to the target 6. By adding more values, the window is going to grow larger and larger. It's not going to ever get smaller. We're never going to reach the target starting from here. So at this point, we know we have to shrink our window for us to ever get another valid window. So what we're going to say is starting from here, what's the minimum length window that would sum up to the target 6? So what we would do is take our left pointer and then increment it. And after we've done that, we can go to the next iteration of the loop where our right pointer now is going to be shifted over here. And this is the next value that we're adding to our sum. By the way, when we shifted our left pointer, our sum was 6. But when we remove this value from the window, we take that value, which was a 2, and then decrement it from our window. So now our window is a sum of 4. Notice how we didn't have to go through every value to recalculate that. We were keeping track of the total sum. When we remove one value, we can just decrement it from the total sum. And now that we're going to another value and adding it to the window, we're going to simply add that 2 to our total sum. So our total sum is now 6. Once again, we reach the target, but the window is of exactly the same length. So our minimum window length is still 3 for now. But once again, we're going to shift our left pointer by 1 to be over here now. And now our window sum was 6, but we removed a 3. So now our window sum is equal to 3. So now once again, we're going to go to the next iteration of the loop where our right pointer is going to be incremented. So our sum is 3, but we're adding a 4 to our window. So now our sum is going to be 3 plus 4, which is equal to 7. So that is not equal to the target, but it's okay because we're only looking for sums that are greater than or equal to the target. So this is technically a valid window. But we want to find the smallest window possible, which is exactly why we're going to now take our left pointer and then increment it, but we're not necessarily only going to do it once. Right now we just removed a 1, so therefore our total sum is now going to be 6. And our left pointer is going to be over here. This is also a valid window. The sum is 6, our target is 6, and now this is actually the new minimum window. It's of length 2. But since the sum is still greater than or equal to the target, we're going to keep shrinking this window. We're going to take the left pointer and once again increment it. Now it's going to be in the same position as the right pointer, and our sum is now going to be 6 minus 2, which is going to be 4. So now this window is no longer valid. And things have gotten a little messy, so I'm going to clean it up a little bit. So our left pointer would be all the way over here, same as the right pointer. And then we would now increment the right pointer one more time. And this would be the new window. The sum would now be 7. It's greater than or equal to the target. So this is a valid window. It's of length 2, which was the same minimum length that we calculated earlier. So now we would try to increment our left pointer, remove this. So 7 minus 4, our sum is 3 now. This is our window, and it's no longer valid. So then we would try to increment our right pointer again. It's out of bounds. So that's how you know we can stop. So now let's take a look at the code, and I'm going to explain to you why the time complexity is still big O of n. So we initialize our left pointer all the way at the beginning. As with most sliding window problems, our total is initially going to be 0. You could also call that our current sum, like our window sum. Our length is initially going to be positive infinity because we're trying to minimize it. So by setting it to a really big value, when we run our min function, we will end up reducing it. You could also initialize the length to be the length of the input array plus 1. That would also be a good default value. And let's assume that in this example, if we never find a window that has a sum of greater than or equal to the target, we end up returning 0. And we would know that because our length would still be the default value that we set it to, which in this case is positive infinity. So if that was the case, we would return 0 as us indicating we could not find a subarray. But if we do find a subarray, we return the length of it. Now the code isn't super crazy. We have a left pointer. As we take our right pointer and keep shifting it, we're adding that value to the total current sum. If the current sum ever is greater than or equal to the target, that means we have a valid window. So the first thing we're going to do is take the length of that window and check, is it smaller than the current length that we've calculated so far, the current minimum length? If it is, we reassign the current minimum length. That's step 1. Step 2 is where we try to shrink our window. That means we take the left value over here and subtract that from our total, just like I was doing earlier. Here, our total would be 6, so we're going to subtract 2 from it, and now it's going to be 4. We're also going to take that left pointer and then increment it by 1 to be over here. So we're going to continue to do this until our window is no longer valid. The reason we're doing it is because, remember, our goal here is to find the minimum length subarray. So as we keep shrinking the window from the left, we're finding the smallest possible subarray. And the rest of this walkthrough would play out just like we talked about a second ago. So this sliding window solution is a linear time algorithm, but the code can be confusing because normally when we have nested for loops, we're kind of trained to think that that is an n squared solution, but in this case, it's not. Let me explain to you exactly why. We have an outer loop. We know for sure that the right pointer is going to visit every single position in the input array. We also know that the left pointer is possibly going to visit every position. It's going to start at the beginning and it's going to be incremented in some cases when the inner while loop runs. But the left pointer might not necessarily reach the end of the array. Let's suppose that in this case, our target was actually a really big value like 60. So in that case, our left pointer would start here and the inner loop would never run because our total would never be greater than the target. But in the worst case, as we showed a second ago, when our target is 6, our left pointer would have been in this position and in this position and in this and all of these. So what I'm saying here is that looking at this, it's clear that the time complexity is roughly 2 times n, which we know reduces to big O of n. So how can that be possible when we have an inner loop? Well, the thing with this inner loop is it's not always going to execute. When our right pointer is over here, our left pointer is still going to be over here. When our right pointer is over here, our left pointer is not going to be changed. It's going to stay exactly where it is. When our right pointer is over here, our left pointer is going to be incremented once because our total sum was equal to the target. So we had to shrink the window. So then we move it over here. When our right pointer is over here, once again, our sum was equal to the target. So we increment the left pointer and move it over here. When our right pointer was over here, our sum was once again greater than or equal to the target, so we incremented our left pointer once, and then actually it was still greater than or equal to the target, so we incremented our left pointer twice. What we're starting to notice is in some cases, the inner loop ran once. In other cases, like over here, the inner loop never ran. And in some cases, like over here, the inner loop ran multiple times. Finally, when we're finished, when we get to this point, our left pointer was once again shifted by 1, but our left pointer was still shifted only n times. That means the inner loop runs a total of n times, not n times for each iteration of the outer loop, but n times total. I hope this makes it clear why even though we have an inner loop, the time complexity is still big O of n. It's about the total number of times that the inner loop is going to execute. And as I just showed, it's only going to execute a total of n times. So this is the general pattern and generally what the code looks like when you have a sliding window solution where the window is of variable length. You usually have an inner while loop, but that doesn't mean the time complexity is worse than big O of n.